Now let's talk about the bifurcation buckling analysis. We will do it by using the beam column elements that we derived and the shell element. Now this analysis type is used for calculating the buckling load of a particular member or a structure, and it's mainly used for straight members. Now imagine that we have a column and we are applying an axial load to it, and this is a perfect straight column. Now let's plot the load deformation curve. And let delta be the lateral deflection. Okay, so in theory, when you apply an axial load like this is what we see. And this continues until P is equal to P critical. Now, after that, we have two equilibrium paths. One of them is, since this member is perfectly straight, it can go this way. But remember that when P is equal to P critical, this column has no lateral stiffness. Okay, since it has zero lateral stiffness, this is also an equilibrium path. So at this point, we have a bifurcation point. Let's repeat. Now here at this point, there's no lateral stiffness, meaning that any lateral deformation doesn't violate the equilibrium condition, because we will not see any lateral forces, internal forces in there. Okay, so this path also satisfies the equilibrium, and we got these two paths, and at this point we have a bifurcation point. Now let P is equal to lambda times P applied. And as the name implies, this is the applied axial load. Axial load on your column. So we can say that the stress stiffening matrix, or the initial stress matrix, geometric stiffness matrix, will be equal to, since it is linearly proportional to the axial load on your member, we can write the same thing as lambda times stress, the geometric stiffness matrix, due to applied loading. Now at the bifurcation point, so we should apply this K plus, let's call it lambda critical because we are at the bifurcation point, K times geometric stiffness due to the applied force, multiplied by the displacements, whatever displacements we have. Again, this is due to applied, should be equal to lambda critical times P applied, right? So this equilibrium condition must be satisfied. So in other words, what we are saying here is we have an axial load P. I'm just showing it as lambda critical at P for this point. And the internal force, the axial forces on this member, should resist that P. So that's the equilibrium condition. Now let's say that the buckling displacement. Let's call it delta U occur relative to U. Okay, so I'm talking about this. Now remember, we are at this point, we satisfy the equilibrium and we can have gamma U in this direction. Okay, we already have U up to this point. After that, we can have delta U. Now, since the applied loading doesn't change at the bifurcation point, we can write the following equation. K times lambda critical geometric stiffness due to the applied force multiplied by U due to the applied plus delta U should be equal to lambda critical times P applied. So this equation should also hold. So we have two equations. So let's subtract equation star from the equation 1. I got K plus lambda critical multiplied by the geometric stiffness matrix multiplied by the displacements, buckling displacements, should be equal to 0. So we know that this one is not equal to 0. Then the only possibility for this equation to hold is this K plus lambda critical times the geometric stiffness matrix due to whatever loading we have on the system must be equal to 0. And we know this type of problem. This is an eigenvalue problem. So we calculate the eigenvalues of this equation. And when you solve the eigenvalue problem, the smallest eigenvalue, let's call it lambda critical, is the scale factor that defines the level of applied that causes buckling. Okay, so you have a loading on your system and then you solve the eigenvalue problem and you get an eigenvalue. The eigenvalue tells you this: when you multiply the eigenvalue with the applied loading, just a linear scaling up, you get your buckling load. And the eigenvector of the corresponding lambda critical gives the buckled shape. Sometimes we call them buckling modes. So that's it. You calculate the elastic stiffness matrix, and then by using the results, you calculate all the internal forces. Using the internal forces, then you calculate the geometric stiffness matrix for the whole system. And then you perform an eigenvalue solution and calculate the lambda critical. The smallest eigenvalue will give you the scale factor. You multiply this scale factor with whatever loading you have on the system, and you get your buckling load, the load that causes buckling in your structure. And the corresponding eigenvector, if you plot it, you'll get your buckled shape. Now let's take a look at some examples and see how this works. Now let's take a look at how we can perform bifurcation buckling analysis. Now in this case, we are modifying the frame analysis program that we wrote. So here I'm adding a geometric stiffness matrix. So this is the matrix that we derive for the beam column elements or just the frame elements. Now the local stiffness matrix calculation is no different. So I added another algorithm that calculates the geometric stiffness matrix, but this algorithm of course needs the axial force on a particular member. So the rest you calculate the rotation matrix. So I generated a K global algorithm, so I'm inputting a flag. So if the flag is equal to 1, it will give me just the linear stiffness matrix. If the flag is 2, it will just give me the geometric stiffness matrix, and flag is 3, it will give me the summation of these two. So what we do here is, if the flag is equal to 1, the stiffness matrix is the linear one. Flag is equal to 2, it is the geometric stiffness. Flag is equal to 3, I calculate both of them and add them up. Now all these matrices are in the local coordinate system, so I have to calculate the rotation matrix and then calculate the stiffness matrix in local coordinates to the stiffness matrix in the global coordinate system. Now I have to have these additional algorithms as well, because for the bifurcation buckling analysis I have to perform a linear static analysis first and then calculate the displacements. From the displacements, go to the element displacements. This is what this algorithm is doing. From the global displacement, it will give me the displacement that belongs to a particular member, and then it calculates the axial force of that member. So here I'm calculating the displacement of a given element. So this algorithm does it for every element actually. And then it calculates the rotation matrix, the local stiffness matrix, and then rotate the global element displacement into local, multiply it with the local stiffness matrix, you get the force vector, and from that force vector I only need the axial force, which will be the first row of that matrix. So P is the axial load on the member. So this calculates the element resultant forces in the global coordinates. So basically you get the element displacement, global stiffness matrix. If you multiply the global displacement with the global stiffness matrix, you get the forces in the global, and then you just assemble it and obtain the resultant force vector. In the bifurcation buckling analysis, we will not be using that, but we need it when we start talking about the limit point analysis. This part of the algorithm is exactly the same. Calculate the total number of equations, form the force vector, Now the assembly of the stiffness matrix has no difference. You calculate the K global. If the flag is equal to 1, it will give me the elastic stiffness or the linear stiffness matrix. If I say the flag is equal to 2, it will give me the geometric stiffness matrix. Flag is equal to 3, it will give me the summation of both. Now the bifurcation buckling analysis. So what we do is, again, the start is exactly the same as the linear analysis. Number the equations, force vector, obtain the linear stiffness matrix. Remember that K is equal, flag is equal to 1. So this is the elastic stiffness. Calculate the displacements for this given force vector. And then for every element, I calculate the axial load on them, store it into P. Then use the same algorithm, but this time the flag is equal to 2. Now I'm inputting the P as an input and then get the geometric stiffness matrix. So now we have the linear stiffness matrix, we have the geometric stiffness matrix, and we need to solve the eigenvalue problem. Remember that the way we formulate the eigenvalue problem is as follows. Let's write it in here. So we say that K plus lambda times the geometric stiffness matrix must be equal to 0. So we can rewrite it as follows. Identity matrix times lambda times K inverse times K sigma must be equal to 0, and this is our A matrix. I'm multiplying it with minus so that we will get the positive eigenvalues as the scale factors. And then I get the eigenvalues, calculate the eigenvalues, the eigenvectors. I'm interested in the positive eigenvalues, so I am just calculating, going over all the eigenvalues that I calculated, store the ones that are positive and report them. And we said that the eigenvectors will give us the buckling modes. So I'm just using this Hermitian shape functions. So this is the equation that gives us the deformed shape depending on your displacements. And this is the plot algorithm that we use in the previous homework. All right, now let's take a look at an example problem. This example problem is from the AISC code. It's a benchmark problem to check the software, if the software works can perform geometric nonlinear analysis. So it gives the results, the analytical results for several cases. So I just take it as an example. So this is the major axis bending, and that's the property of the section. And for that section, this is the moment of inertia, this is the area, and this is the elastic modulus. So all units are consistent. So these are the coordinates, connectivity, and the material matrix. So since this is a cantilever, the earlier buckling load is pi square EI over KL squared. Now K is equal, for this element, since this is a cantilever, K is equal to 2. So from the earlier buckling load, the theoretical buckling load for this cantilever is 1369 kilonewtons. Now let's see if we can obtain the same result by performing the bifurcation buckling analysis. So here I am performing a buckling analysis, and these are the eigenvalues. And when you look at the eigenvalues, the first one is 1380. Now as a loading, what I did is this: I take the cantilever and apply a unit load, a point load here. So this is the force vector. Okay, this is equal to -1. And in that case, the eigenvalues, the scale factors, will directly give me the buckling load. Okay, so we said that in order to obtain the buckling load, take this eigenvalue, multiply with whatever loading you have, and this will be the buckling load of the whole structure. Now, since I added a unit load here, this is the eigenvalue that I obtain, which is directly gives me the buckling load, and the buckling load that I obtain is 1380. And these two results, the analytical results and the bifurcation buckling analysis results, are very, very close to each other. Now let's take a look at the buckling modes. So the first buckling mode is the one that we expect, which has the smallest eigenvalue, is the typical buckling load, that half sine wave. The magnitude is 1380. Now we saw another buckling mode, and it is we have double curvature in this element, and the load that is required to do that is 1700-860. But in actual structure, we will never see that, because the structure will always fail in the first buckled mode. Now, let's take a look at how we can analyze a frame. So it's the same thing, but the buckling load is a little bit tricky. So the frame that I'm solving is this. The boundary conditions, this is fixed. This is fixed as well. So this distance is 8 meters. The height of the columns are 4 meters. And I'm applying a unit axial load on both columns. Let me redraw that. Okay, so what I'm expecting to see is the buckling analysis, the bifurcation buckling analysis will give me a single lambda value. It means that if you multiply this lambda with these values, you will get the buckling load, the load that causes buckling of the whole structure. So when we do that, this is the P critical, and I obtain two P critical values, and the smallest one is this 3130. If you apply a force that is equal to somewhere here, you are very close to the buckling load. And these are the deformed shapes. This is and the eigenvectors are all in the global direction. So if you want to plot how this frame buckles, you have to plot the deformed shape by using these values. Now let's see how we can perform bifurcation buckling analysis with the shell elements. So here again I will be using the shell elements that we formulated, but I made a small change. This shell element is composed of a bilinear thick plate element and a bilinear membrane element. I also added the drilling degrees of freedom by just adding the small stiffness to the drilling degrees of freedoms. Okay, now alright, so this part is exactly the same, there is no difference. These are the bilinear shape functions, integration with respect to the Cartesian coordinate systems. So for the thick plate element, this calculates the B matrix. For the banding, this calculates the B matrix. For the shears, we have the moment curvature and the shear relationships. So for the banding, I'm using 2-point integration. I obtain the stiffness matrix for banding, and for the shear is single point integration to eliminate the shear locking and obtain the shear matrix, stiffness matrix for shear. Now and then the membrane part will be modeled with the bilinear membrane element. Now the strain displacement matrix is nothing different here, is exactly the same as before. So I made a twist, so I added some stiffness coefficients, a very small numbers, to the drilling degrees of freedoms. Do I have to do it for the bifurcation buckling? No, but I just want to write a code that is general for all types of shell elements. And then we have the equations for routines for the obtaining the element stiffness matrix. This is for the membrane banding element. So we start with an 8x8 and then add the drilling degrees of freedoms to it. Now we have the force vector. This part is the same. Now let's take a look at the geometric stiffness. That part is new. So we need the G matrix, right? G matrix is del n over del x and del n over del y. So I have to put these values in the correct places. So for the shell element, our displacement vector is as follows: u1, v1, w1, theta x, theta y, and theta z, and it goes like that. So here I'm just considering the w1. I'm looking at the w1 interpolation, and for the bilinear thick plate element, it's a linear interpolation. So that's why I'm just putting the derivatives to the third, ninth, and so on to these columns. Now row wise it's 7 and 8 because the force matrix that I will create is as follows: fxx, fyy, fzz, fxy, fyx. So we have the fzx, fzy, and so on, the same here. So again, another 3 by 3, another 3 by 3 here. Okay, so that will be the full stiffness stress matrix for the whole shell element. Okay, so I'm only interested in multiplying with this part because these belongs to the membrane actions u, v, and this part will belong to the w, and I will only multiply these numbers with fxx, fxy, fyx, and fyy, and for us these are all 0. I mean, you can put the z's here, but I don't have any values corresponding to them. So I'm just multiplying the G matrix with these forces. Now I need the membrane forces, so this is where I calculate them. So I'm getting the B matrix, B times U times T gives me the, B times U give me the strains, multiply with the material matrix give me the stresses, multiplied with T gives me the forces. And this is where I calculate the geometric stiffness for the shell element. So we need the element displacements. Okay, by using the element displacements, I'm obtaining the membrane forces. I get the G matrix, and then I'm filling up the S matrix. The S matrix is the one that I just described. It will be a 9 by 9 matrix, and I have these stress matrices, or in that case I use the force matrices here. Okay, so that's the way I assemble them, and by doing that operation, doing the integration, numeric integration, I'm obtaining the geometric stiffness matrix. So this part is very typical to the shell elements. Calculate the rotation matrix. I have a subroutine to convert the xyz coordinate into planar coordinates, xy coordinates. This is what this subroutine is doing. It's a flat shell element, so I have to do mapping, membrane mapping, and the plate mapping. And we have the structural stiffness matrix in global coordinates. That's a long subroutine, but it doesn't do anything very fancy. So I calculate the rotation matrix, convert them into planar coordinates. Here I'm just creating a 24 by 24 rotation matrix. I call it RR. And then I come here. For every element, I'm obtaining the displacements, nodal displacements in global coordinates, multiplied it with R matrix, obtaining the nodal displacements in local, but I will only need the membrane displacement so that I can calculate the membrane forces. So here I'm just extracting the membrane displacements and put it in this UM. And then this is the membrane stiffness matrix. This is the bending stiffness matrix, shear stiffness matrix, and this is the geometric stiffness matrix that uses UM to calculate the membrane forces and obtain the geometric stiffness matrix. So that's the plate stiffness. You add KB and KS, bending and shear stiffnesses, obtain the plate stiffness. And then here I'm assembling the membrane matrix into the shell matrix. assemble the plate matrix into the shell matrix. Now rotate the shell matrix and obtain the K shell. Okay, I need the geometric stiffness matrix as a separate matrix for the bifurcation buckling analysis. So I'm just doing the same thing, do the rotation. This is in local, convert it into global. And in this, the way I calculate the geometric stiffness matrix is for the full shell element. It's a 24 by 24 matrix. So I obtained the shell element in stiffness matrix in global coordinates, shell geometric stiffness in global coordinates for a member, and then I do the assembly and obtain these two matrices, linear stiffness, geometric stiffness. Again, the bifurcation buckling analysis is the same. First, you perform a static analysis. Okay, so I perform a static linear analysis, equation number, force vector, form the global stiffness, and use the first one, this K, to obtain the displacement. Call that algorithm one more time. Instead, now we have the displacement, non-zero displacements, and the second row of that output is the geometric stiffness matrix. Perform the eigenvalue solution. Of course, this is not computationally the best way of doing it, but our aim is not here to develop the best computational algorithm. This is the elastic stiffness inverse multiplied with the geometric stiffness and calculate its eigenvalues. Here I'm just dividing it with 1 to get the scale factor and then present it. And I'm only looking for the positive eigenvalues. So again, for this, to test this algorithm, I'm using our 5-element solution, the typical cantilever that we have. So in order to obtain the buckling load, I apply compressive forces as follows, 0.5 and 0.5, and then perform the buckling analysis. This is the result of the buckling analysis, so it has to be 27,906 kilonewtons. And this is the analytical results. Again, I'm using the P Euler is equal to pi square EI over KL squared. And as you see, we get very close results. I see other buckling modes, but of course, as we discussed, this is the one that we will see. This is the bending mode, the way it buckles as it bends. And again, we obtain very close results.